So today we're going to learn about the mean value theorem, and how we're going to start off is we're going to start off by learning a specific case called Rolle's theorem. Okay. So Rolle's theorem states that if you have a function that satisfies these three conditions, number one, the function is continuous on a closed interval or over a closed interval. So, there's no asymptotes, there's no weird jumps, there's none of this happening. It's a nice, smooth function. At least smooth enough to allow you to differentiate once. And number two is a part of that. Okay, so there are no breaks and there are no weird corners or anything. So it's continuous and you can differentiate it once. And the third requirement is that the two endpoints are at the same level. So the two endpoints of the interval they produce the same function value. That function value could be, it could be negative 100, as long as it's negative 100 on both of the endpoints of the interval. It could be 999.4, as long as it's that value on both sides of the interval. If those three conditions are satisfied, then you can guarantee that there is some number on the inside of the interval, not the edge, but the inside of the interval, such that the derivative is 0. So we'll look at a couple of graphs. We'll draw some. And this is where you can actually, it doesn't actually matter what graph you draw. So you can just make something up, as long as it's continuous and, it's differentiable, and the two endpoints are at the same height. Okay. So let's say on each of these graphs there's an interval that goes from A to B. And whatever level you're at when you're at the endpoint A, you're at the same level when you're at the endpoint B. Like these are the same. Now just draw any function that connects these two endpoints. It doesn't matter what, as long as it's continuous and differentiable. Okay. Whatever function you drew, there should be some sort of turning point. Well, either that or it's completely flat. Either it's completely flat, or if it's not, that there's some turning point where the derivative would be 0. And for this graph, that's right about here. So here f prime of x is equal to 0. And whatever value that occurs at, we can call that C. So I guess really this should say f prime of C equals 0. And this is going to happen no matter what function you draw. Again, as long as it satisfies those three conditions. I mean, you can try your best not to have this happen, but it's gonna no matter what. Because somewhere, you know, you're either gonna have a straight line, right? And if you don't have a straight line, eventually you're gonna deviate in a way that you're gonna need to come back from, and when you come back from it, it's gonna create that sort of turning point that is gonna cause your derivative to be 0. It's going to create that sort of maximum or minimum if you're going, you know, down first and then up. So f prime of C will equal 0 here. And it can happen multiple times, but it is guaranteed to happen at least once. So here's an example where it happens multiple times. Call this C2. Call this C1. Okay. And there's really just no way to keep it from happening. It is guaranteed. So obviously the graphs you draw don't have to be these exact 4 graphs, but this will happen no matter what you draw. What the general proof is. The equation has one solution. Okay. All right. One important thing to note is that Rolle's theorem, and later on the mean value theorem later on doesn't actually give you any information about where C is. It just tells you that it exists somewhere between A and B. well, I mean, I guess it tells you it's between A and B, but it doesn't really help any more than that in determining where C is, just that it exists somewhere between A and B. Right, so it's just another one of those, kind of like the intermediate value theorem. It's just one of those existence theorems. Okay. But one way you can use the mean value theorem, and by mean value theorem I mean Rolle's theorem because that's what we're talking about right now, is to prove that there is not more than one root of an equation. Okay, so we're going to prove that the equation x cubed plus x minus 1 equals 0 has exactly one real solution, no more and no less. So first, proving that there are any solutions at all, we can actually use something we learned before. We can use the intermediate value theorem. Do that exactly. That's something really stupid here. Okay, all right. So we're going to use the interval 0, 1. There's no real reason we're using that interval, we just are. Okay, so we let this be a function. And then we measure the function value at 0, and then we measure the function value at 1, because those are the two endpoints of the interval. Now if we plug in 0 to this function, we get negative 1. If we plug in 1 to this function, we get 1. This is less than 0. This is greater than 0. So somewhere in between, x equals 0 and x equals 1. Or in other words, on the interval 0, 1. So somewhere between 0 and 1, this function x cubed plus x minus 1 is equal to 0. So at least one solution exists. And to prove that it's exactly 1 and not, 2 or 3 or 4 or 500, that's when we're going to use Rolle's theorem. So to prove exactly one solution, I mean, obviously this isn't going to be a proof-based calculus class, but there's no reason you can't be exposed to them early on. We're going to do proof by contradiction. And what that means is that we're going to suppose that the thing we're trying to prove is false. So we're trying to prove exactly one solution exists, and not more. So to do this proof by contradiction, we're going to start off by assuming that more than one solution exists. Then f of, let's say, C1. No. Gosh, what letter should we use? Okay. And there are two x values, a and b, that are solutions. And if they're solutions to that, then the function value should be 0 on both of them. But the function values being the same is the important part. So since f is continuous and differentiable, and there are two places where the function value is the same, supposedly, we're assuming that, then Rolle's theorem should apply. So there should be a value c with the implication being that it's somewhere between 0 and 1. Well, actually, somewhere between a and b, where f prime of x equals 0. And let's see if that's true. Now, f prime of x is going to be, from the power rule, 3x squared plus 1. Okay, so take 3x squared plus 1 and set it equal to 0. You're going to get, first of all, 3x squared equals negative 1. Then x squared equals negative 1/3, which has no real solution. Which contradicts exactly the last thing that we concluded. there should be some value where f prime of x equals 0, and yet there is not. Everything else before then was sound, so our assumption is wrong. There can't be more than one solution. So now we know that there is exactly one. Because if there was more than one, then that causes a contradiction. Simultaneously, there should be a value where the derivative is 0, and also there isn't. So there cannot be more than one. So you can use Rolle's theorem and later on the mean value theorem for things like this. The existence of or the non-existence of multiple solutions to a function. Okay. So first we're going to verify that Rolle's theorem even applies to this function and this interval. And then we're going to look for those places where the derivative equals 0. And honestly, well, you could start immediately by just taking the derivative and setting it equal to 0 and seeing if you get any values from, that are in between -4 and 4. Totally could. I don't know where I was going with that sentence, actually, because you totally could just take the derivative and set it equal to 0 and try to see if any values are in between -4 and 4. But first you want to know that you're not wasting your time trying to do that. So just do a real quick check that f of x is continuous. Now, since it's polynomial, it is. And likewise, because it's polynomial, it is also differentiable everywhere. Even though technically we just need it to be differentiable on A and B. And does f of A equal f of B? Well, if we plug in -4, we get -64 minus 64, so -128, plus 64, so -64, plus 3, so -61. And if we go ahead and plug in 4, we get 64 minus 64 minus 64, so -64 plus 3, so also -61. Okay, so Rolle's theorem applies, and there is guaranteed to be at least one value in between -4 and 4 where the derivative is 0. So there's a C somewhere in the interval, A A to B, where f prime at C is equal to 0. Then what is C? So although we have to prove its existence, eventually it just becomes sort of finding a horizontal tangent line, the same as one of those problems. Okay, so f prime of x, let's find the derivative in general first. That's going to be 3x squared minus 8x minus 16. And we'll set that equal to 0. If I think about you multiply the 3 and then minus 16, you multiply a and c, and try to find out what two factors of negative 48 are going to add up to negative 8. I think of negative 12 and positive 4, and then divide each one by 3, minus 4, and then 3x plus 4. Okay, so this should factor into 3x plus 4 and x minus 4. I think that sounds about right. So that'll be plus 4x minus 12x, yeah. Let's get these two solutions from there. X equals 4 and x equals negative 4/3. Now x equals 4 doesn't count because it's not inside of the interval. It's not inside of the open interval from negative 4 to 4, right? It's one of the endpoints. It's on the edge. And that's not really what Rolle's theorem is talking about. Rolle's theorem is talking about there being some x value on the inside of the interval where the derivative is 0. So really, it's the specific x value that it's talking about is the negative 4/3 x value, not the positive 4. Okay, so this doesn't count because it's not on the open interval a to b. It is literally b, right? Which is not included if you're talking about the open interval from a to b. Okay, now we're going to do this with a different function. We're going to do the same. With the function x plus 1 over x over 1/3 comma 3. Let's first verify the three things that you need. Its continuity, its differentiability, and the function being equal at both endpoints of the interval. Now, there is an asymptote at x equals 0, but that's not in the interval, so it doesn't count. And it does turn out that it's continuous from 1/3 to 3 at least. And similarly, because of that 1 over x term, it's not differentiable at 0, but again, that's not in the interval, and it is differentiable everywhere else. So it is differentiable on the interval 1/3 to 3, on the open interval from 1/3 to 3. And are the values at the two endpoints of the interval the same? Yes, they are, because it's sort of like reflexive. You plug in 1/3, you get 1/3 plus 3. Plug in 3, you get 3 plus 1/3. So either way, you get 10/3. So there exists a value c, somewhere in the interval from 1/3 to 3, the open interval, where f prime of c is equal to 0. Now, as for what this graph looks like, you don't need to know what this graph looks like, but it is going to look something like this. It's going to be one of those like rational looking functions, but with a slant asymptote. Let's just say 1/3 somewhere around here, and maybe 3 somewhere around here. So hopefully you can tell that graphically there is going to be, one of those turning points where the derivative is going to be exactly 0, where the horizontal line, where the tangent line is going to be horizontal. Somewhere in between these two endpoints. And you can kind of tell that it's going to be right here. Okay, so f prime of x, take the derivative of x is 1. And the derivative of 1 over x is negative 1 over x squared. And that's from the power rule, right? 1 over x is x to the negative 1. You take that negative 1 power, you multiply it in the front, that makes it negative. You decrease the power from negative 1 to negative 2, that makes it negative 1 over x squared. So both of these just use the power rule. Okay, so from this you can get, by setting this derivative equal to 0, you can get 1 equals 1 over x squared. You can multiply both sides by x squared. No real problem with that. X squared equals 1. So get that x equals negative 1 and 1. Now, while it is true that there is going to be a horizontal tangent line at negative 1, because it's an odd function, so whatever is happening over here is going to happen down here as well, this is not the value that's guaranteed by Rolle's theorem, because we're only guaranteeing a value that's on negative 1/3. That's on the interval 1/3 to 3. So it's actually the interval, the x value 1 that where the existence of a horizontal tangent line is proven by this theorem. So Rolle's theorem in summary, states that if a function is continuous and differentiable over an interval, and as long as the value at the two endpoints is the same, then there should be somewhere in the interval, somewhere in between those two endpoints, where the derivative is exactly zero. Now, this is actually a specific case of a more general theorem called the mean value theorem. And when we talk about the mean value theorem, two things are going to be different. We're still going to look for continuity and differentiability. But we're not going to be looking for the two endpoints to be the same. And we're not necessarily going to be guaranteed that we're going to find some place where the derivative is zero necessarily. So for the mean value theorem, the more general case, we actually only need two conditions. We need the function to be continuous on the closed interval from A to B. So no discontinuities anywhere there. No asymptotes or anything like that. We also need to be differentiable in the open interval from A to B. So it doesn't necessarily have to be differentiable at the endpoints, but we at least want it to be differentiable on the interior of that interval. Then, and there's no other conditions to check. But then what we're guaranteed is that we can find a place, we can find a value C inside the interval where the derivative is equal to the slope of the secant line formed between the two endpoints. If you might notice, this is just a slope formula. It's it's like y2 minus y1 over x2 minus x1. So this is the slope of the secant line between 2 points A comma f of A and B comma f of B. And this is just going to be the derivative at some C that's inside A to B. That's guaranteed to happen. Now, to see how Rolle's theorem was a specific case of this, remember that for Rolle's theorem, we needed f of A to equal f of B. That means if f of A is equal to f of B, that the top of this fraction on the right is zero, like if those two values are equal. And well, that was what Rolle's theorem was. If we added the extra condition that f of A equals f of B, and then we said we should be able to find some place where f prime of C equals zero. But you can go further than that. You don't need to guarantee that f of A equals f of B in order to be able to make use of a theorem like this. Okay. So this is basically saying that what's on the right of this equation, the slope of the secant line, or in other words, the average rate of change between A and B, because that's what that's going to measure, is equal to the instantaneous rate of change somewhere inside the interval. Now, we can draw, just like we did with Rolle's theorem, we can draw any sort of function, and as long as it's continuous and differentiable from A to B, it's going to guarantee this theorem. So just slap down an A and a B somewhere. And you don't need f of A to equal f of B anymore. They can be at different heights, it doesn't matter. And then just draw a function that, connects f of A and f of B. What the mean value theorem states is that because this is continuous and differentiable, there should be some point from A to B where the derivative is equal to the slope of this line, the secant line. The line that directly connects the two endpoints. So the slope of this line, so let's say this y value is f of A, and this y value is f of B. Slope of this line should be f of B minus f of A over B minus A. That's just the slope formula. And based on sort of a quick visual inspection, there do appear to be two places on this interval where the derivative would be equal to the slope of this line. Somewhere over here, and somewhere over here. But notice how the derivative and those derivatives and that slope are equal. The existence of those places where those slopes are equal to where those derivatives are equal to the slope of the secant line are what's guaranteed by the mean value theorem. Say f prime of C1 and f prime of C2. Now, it may turn out that there's just one place that does that, but there can also be more. Okay. Now, you can try to avoid this for, like as much as you want, but you'll find that it's impossible to. Okay, so for example, let's say that the A is, the f of A is up here and f of B is down here. In the same way that we couldn't avoid getting a horizontal tangent line with Rolle's theorem, we just make the secant line first. You're not going to be able to avoid getting a place on the graph whose derivative is equal to the slope of the secant line with the mean value theorem. You can try, but eventually you're going to be forced to connect two endpoints, and there is going to be a place where you get your derivative being the same as your secant line, or the slope of your secant line. And that actually is just a consequence of the continuity and differentiability. You can't make any weird jumps, and you can't make any weird bends in the function. So you're sort of forced to make this this function that somewhere curves just the right amount to have the derivative be equal to the slope of that secant line. So we're going to use the mean value theorem with this function x cubed minus x over the interval 0 to 2. Minus x, huh? It's probably... Okay. So you don't have to draw a graph, but you can. So we're thinking about the interval from 0 to 2. And if we graph this function, we're probably, let's see, 0 will be 0, 1 will be 0. Yeah, that's probably something. That's probably what happens. Okay, so the graph is shaped something like this. Yeah. And it does the same thing on the other side because it's an odd function. But specifically, we're concerned about this. And if we connect the two endpoints of the interval with a secant line, that secant line has a slope. And because it's continuous and differentiable, this function, over the interval at least, we're guaranteed some place in between 0 and 2, where the derivative is parallel to that secant line. The derivative is equal to the slope of that secant line. Basically, the secant line and the secant line and a tangent line are parallel. But where is that? That's, something we'll have to set up. So f of x is continuous on 0 to 2. Oops. And f of x is differentiable on 0 to 2 as well. So the slope of the secant line is given by that expression f of b minus f of a over b minus a. So that's f of 2 minus f of 0 over 2 minus 0. Which, plugging in 2, that just gives you 6. Plugging in 0 gives you 0. For a slope of 3. So that secant line has a slope of 3. Which kind of makes sense. I mean, you're going from a point that, you're going from the point 0, 0 to 2, 6. That's going to have a slope of 3. So the mean value theorem guarantees C where f prime of C equals 3. So it's no longer the specific case of the derivative equaling 0. The derivative can equal whatever the slope of the secant line you have is. But you do this the exact same way. Just instead of setting it equal to 0, you set it equal to 3 instead, and then solve for that value of x. So f prime of x is equal to 3x squared minus 1. And you set that equal to 3. From this, you can add 1 to both sides and get 3x squared equals 4. Divide by 3, get x squared equals 4/3. Then take the square root to get x equals plus or minus 2 over square root of 3. Well, we'll say, as comma separated, let's negative 2 over square root of 3, comma, positive 2 over square root of 3. And given that the negative value here is not on the interval we're talking about, then it must be this. Now 2 divided by square root of 3, it's around 2 divided by 1.7, so that's going to be about, I don't know, it's between 1.1 and 1.2. So this value right here, even if I didn't draw it to scale or like correctly, this value is 2 over the square root of 3. So C is equal to 2 over the square root of 3. And you can rationalize this to be like 2 square roots of 3 over 3. But it kind of doesn't matter how you write it. But the existence of that, even if you can't find it through, algebraic methods, the existence of such a point on the graph is guaranteed by the mean value theorem. Right. Yeah. Okay. Right. Okay, so we're going to do what we just did basically up here with this function. First, we got to verify that it's continuous and differentiable on that interval. So it's got to be continuous on the closed interval. One to 2. And it is. The only possible thing that could be called a discontinuity is at x equals 0, which is not in between 1 and 2. So 1 and 2 is, the interval from 1 to 2 is fine. And it's also differentiable on that same interval for those same reasons. Rational functions are differentiable everywhere that is on their domains. So just not, whatever asymptotes may be there, which, there are none from 1 to 2. So the mean value theorem should apply, should hold. And what we're basically doing is we're working with this function right here. Let's see, okay. So the function kind of looks like this. And we're concerned about the interval from 1 to 2. We're going to make the secant line from 1 to 2. And, there's clearly going to be some place in between 1 and 2 where the derivative is equal to that slope. So we're trying to find that place. So first we got to find the slope of that secant line so we know what to set our derivative equal to. Slope of the secant line. Over 1 to 2. That's going to be f of 2 minus f of 1 over 2 minus 1. It's going to be 1/2 minus 1 over 1 over 2 minus 1. So that's, negative 1/2 over 1, which is negative 1/2. So it's guaranteed to be some value c inside of the interval from a to b, where f prime of c is equal to that that slope of negative 1/2. And we can find that if we take the derivative and set it equal to negative 1/2. So f prime of x is going to be, again, the derivative of 1 over x is negative 1 over x squared. You can just sort of, once you see that enough, once you see the function 1 over x enough and have to take its derivative, eventually you can just remember it's negative 1 over x squared. You don't have to well, hopefully, eventually you won't have to rewrite it as a power of x and then do the power rule and then rewrite it as, without the negative exponents. Just hopefully one day you'll memorize that the derivative of square root of x is 1 over 2 square roots of x. But anyways, you take this, you set it equal to that negative 1/2, and then from there you can get x squared equals 2. Essentially just by taking both sides of this, flipping them upside down, getting rid of the negative, negative 1 on top of x squared equals negative 1 on top of 2, then x squared must equal that 2. And then, if that's true, x must equal negative square root of 2, or positive square root of 2. Except, we're going to get rid of that negative square root of 2 because that's not on the interval from 1 to 2. So it's square root of 2, which is around the value of 1.4. So we now know c is equal to the square root of 2. That's the place, that's the x value where the derivative is equal to the slope of that tangent line, or the slope of that secant line. We'll do one last example, just like this. So basically, this is all the same stuff you've been doing before. You're just, instead of finding places where the secant line, where the tangent line is horizontal, or where the tangent line has a slope of 0, you're just finding where the tangent line has a slope that is a specific number. That specific number being given by the slope of the secant line over an interval. So we're going to do the same thing basically with function square root of x over the interval 0 to 4. Okay, so again, you don't actually have to draw, graph these or anything, but just in the interest of clarity, square root function is going to look something like this. Actually, it does continue past here, but that part's not so important. So if we make the secant line between these two endpoints, that secant line is going to have a particular slope. I'm not sure what that is yet, but if this function is continuous and differentiable, there should be a place somewhere where the tangent line is parallel to that secant line. Okay. The two things you have to verify are continuity over the interval which this function is, and differentiability. Over the open interval from 0 to 4. Okay. Yeah. So the slope of that secant line is given by f of 4 minus f of 1 over 4 minus 1. Now, f of 4, if you plug in 4 into the function, you get 2. If you plug in 1 into that function, you get 1. Over 4 minus 1, which is 1 over 3. So 1 over 3 is the slope of that secant line. And 1 over 3 is the, and therefore 1 over 3 is the value of the derivative that is guaranteed to occur somewhere between 0 and 4. So you're guaranteed some value c.
Isn't A 0?
A is definitely 0. Okay. Yeah. So this is 0, this is 0, this is 0, this is 0, and you actually get 1/2. Okay. Because you get 2 over 4. Thank you for that. Let's see, we're f prime of x, well, we're f prime of c, right, is equal to that 1/2. So since you guarantee that, you get to take f prime of x and set it equal to 1/2 and find out where that happens. So f prime of x is going to be 1 over 2 square roots of x. Again, because of the power rule, if you write x as 1/2, if you take the 1/2, you multiply it to the front, that creates the 1 over 2, and then you decrease the power by 1 down from a power of 1/2 to a power of negative 1/2. So it exists, still has a square root, but on the bottom. So 1 over 2 square roots of x. And you just set that equal to 1/2. The numerators are the same, so the denominators must also be the same. You can get 2 square roots of x is equal to 2, or square root of x is equal to 1, or squaring both sides, that x is equal to 1. Which is on the interval from 0 to 4. So that place where this happens, c is equal to 1. So at x equals 1, the value of the derivative is going to be 1/2, the same as the value of the secant line from 0 to 4.